Contrary to what many people think, the universe is not only comprehensible, but it actually makes sense. As we learn more about the universe, things that once didn't quite hang together now seem increasingly logical, certainly more so than human affairs. This video describes a theory called the zero-energy universe. Over time, evidence is accumulating that the universe contains two kinds of energy that are in exact balance, and more importantly, that balance was required for the universe to have come into existence in the first place. Let's start with a familiar equation by Einstein. This equation basically says that mass and energy are interchangeable aspects of something called mass energy. Now for a basic rule that's never broken, the so-called first law of thermodynamics. Mass energy cannot be created or destroyed, only changed in form. This is the law's present wording, updated since Einstein proved the equivalence of mass and energy. Remember this law going forward. The evidence for it is very good, and it plays a part in the birth of the universe. As the so-called first law became accepted, as evidence accumulated for it, people began to wonder how such a logical, consistent universe could violate its most basic rule in order to come into existence. Doesn't the Big Bang, the birth of the universe, create something out of nothing? Isn't the universe a giant free lunch? Over time, this question led to the idea of the zero-energy universe. There are many kinds of energy, but in this section we consider two: kinetic energy, the energy of motion, and gravitational potential energy, the energy that draws masses together. Imagine a rocket lifting off. To do this, it must overcome the pull of gravity drawing it toward the Earth. As it ascends from the planet, the rocket expends kinetic energy to overcome gravitational energy. When the rocket gets to its destination, it encounters another rocket that didn't expend the same energy. How do the rockets differ? Where is the energy accumulated by the traveling rocket? The answer is to understand that gravitational energy is negative. And when a rocket leaves the Earth, its positive kinetic energy overcomes negative gravitational energy, and the sum of these energies becomes zero as the rocket approaches infinity. Negative gravitational energy answers many questions. One, it meets the common sense observation that widely separated masses possess little gravitational attraction. And two, an ascending rocket's gravitational energy increases by becoming less negative. Here's a table of orbital classes, each defined by the ratio of kinetic to gravitational energy. If an orbit's kinetic energy is 1/2 its gravitational energy, the orbit is a circle. As this energy ratio increases, between 1/2 and 1, the orbits become increasingly elliptical. And when the ratio of kinetic to gravitational energy equals 1, something very interesting happens. First, as I will show in the next section, this solution is an escape path. The craft departs, never to return. Second, because gravitation is negative, and because kinetic and gravitational energies have the same magnitude, they sum to zero. So in this fascinating solution, the separate kinetic and gravitational energies are non-zero, but their sum is always zero everywhere on the path. And as the escaping body approaches infinity, the individual kinetic and gravitational energies decline toward zero. Not to jump ahead too much, but this zero-energy escape profile turns out to have important consequences in modern cosmology. Negative gravitation solves other, less obvious problems. An orbiting body in the vacuum of space, not experiencing friction or collisions, should neither gain nor lose energy as it orbits, consistent with the first law. But this is only possible if the positive kinetic energy of motion is balanced by the negative potential energy of gravitation. Before I show my orbital model results, a word of explanation. To calculate spacecraft and planetary orbits in systems with more than two bodies, we must accommodate the so-called three-body problem, which says that no general solution exists for orbital systems with more than two bodies. Isaac Newton first discovered this and was unable to find a solution. Since Newton's time, we've discovered there's no general solution. All orbital problems with more than two bodies must be calculated step by step using numerical methods. When NASA calculates a spacecraft path to Mars, they do it step by step in a numerical model. I created this video's orbit animations with just such a model, one that lets me track kinetic and potential energies and test whether energy is conserved. Now let's explore an orbit that shows the interplay between kinetic and gravitational energy. Here's my model for an Artemis-style mission to the Moon. In this model, as in reality, a single rocket burn moves the spacecraft from Earth orbit to a lunar round trip with a free return path. Free return means no additional rocket burns are required to return the spacecraft to Earth. My orbital path isn't the one used by the Artemis program. Mine is less complex, but takes more time. I think NASA rejected this path because they would have had to pay the astronauts overtime. Just kidding. Here's a version that tracks energy as the orbit proceeds. It shows the gravitational energy from both Earth and Moon, the spacecraft's kinetic energy in red, and the sum of all of them in yellow. Notice about the yellow bar, the energy sum, that it doesn't change, even though the spacecraft is experiencing many changes in velocity and gravitational energy from both the Earth and the Moon. This interplay between Earth, Moon, and spacecraft with a constant net energy shows that the universe obeys the first law. In this complex orbit, with multiple energy sources, energy is not being created nor destroyed, only changed in form. Notice that this outcome is only possible because gravitational energy is negative. Mathematical models like this let scientists confirm or refute our theories about the universe using detailed orbital data. Then, because the models are confirmed in space missions, this increases our confidence that we're on the right track. Here's a different solution that, strictly speaking, is not an orbit, but an escape path. If I model a spacecraft burn that causes kinetic and gravitational energies to be equal, the spacecraft departs, never to return, and the escape path net energy is zero. This profile is called escape velocity. It's not an orbit, but a parabolic no-return escape path. Because it has zero net energy, this solution plays an important part in orbital mechanics and physics, and may explain how the universe came into existence. More on this later. Here are more detailed orbital models. These models show a correlation between the ratio of kinetic to gravitational energy and the shape of the orbit. Here's a circular orbit, sort of like the orbits of Earth and Mars. Notice that this orbit's kinetic energy is about half its gravitational energy. Here's an elliptical orbit, like comets and some asteroids. Notice about this orbit that even though the energy values change dramatically during the orbit, the sum of kinetic and gravitational energies remains the same. Unless an orbiting body collides with something, this must be true. The first law requires it. Now let's revisit the escape path solution. As before, if I set an orbit's kinetic energy to equal gravitational energy with opposite sign, the orbiting body follows an escape trajectory. In this graph, I drew two bodies to more clearly show the parabolic shape of the escape path. This is the only path in orbital mechanics that has this shape. Even though it can configure many different starting directions, the outcome is always a parabola, and the craft always escapes. Here's the same model at a larger scale. Notice about these animations that, regardless of their initial launch direction, the bodies always follow a parabolic path, and they always escape. Now try to imagine all the objects in the universe moving along with the expanding universe itself at exactly escape velocity, all with zero net energy. Not to get ahead of myself, but the zero energy universe idea requires that the universe not only expand, which is well established, but at a particular rate, escape velocity. The zero energy escape path is a beautiful bit of physics and mathematics. I think pure mathematicians, number theorists for example, have more chances to encounter mathematical beauty, but we applied mathematicians sometimes find examples of mathematical beauty, and this is one of them. The escape path profile is easy to describe. A mass is given a kinetic energy, a velocity, equal to its gravitational potential energy, but opposite in sign. At first, the kinetic and gravitational energies are high, but over time they decline, perfectly in step and always summing to zero. As the craft approaches infinity, the individual energies decline to zero. Importantly, at every point on the path, the net energy, the sum of kinetic and potential energy, is exactly zero. It's a beautiful result. This solution may answer a basic question about the universe. At the moment of the Big Bang, if the universe's mass and energy began with exactly escape velocity, that would mean zero net mass energy for the entire universe, so the Big Bang would itself honor the first law of thermodynamics. And my models confirm the first law. It shows that a system that starts with zero net energy always has zero net energy. In the early 20th century, the universe was thought to be static, unchanging in size. When Albert Einstein created general relativity, he realized such a universe would collapse under gravity, so he introduced a repelling force later called the cosmological constant, to keep the universe from falling in on itself. Since then, two things have happened. One, recent research shows that the cosmological constant wouldn't have worked. Because of an issue much like the three-body problem, the universe would have collapsed under gravity anyway. And two, by the late 1920s, we realized the universe was expanding, so the cosmological constant actually served no purpose. And in more recent times, evidence is accumulating that in order to exist at all, the universe must be expanding at exactly escape velocity. One may ask, even if it meets the net zero energy requirement, how can a universe just pop into existence? To answer that question, we must visit the world of quantum physics. Quantum physics isn't at all like classical physics, the kind described by Einstein and others. In classical physics, a particle either exists or it doesn't. If a particle ceases to exist, its mass and energy are converted to another form, and the universe's account books remain balanced. About quantum physics, Einstein famously said, "God doesn't play dice with the universe." For once, Einstein was wrong, as demonstrated by, among many other things, modern computers, which rely on a number of quantum effects. I won't try to explain quantum theory here. I'll just say that quantum allows, no, demands, the existence of virtual particles, particles that appear and disappear without upsetting the energy bookkeeping of the universe. Remember the first law that says mass energy cannot be created or destroyed, only changed in form. As spooky as it is at times, quantum theory obeys this law. Virtual particles come into existence and disappear again, but never break the first law. In fact, we live in a sea of virtual particles, a fact that has few observable effects. One is called the Casimir effect. If you position two metal plates next to each other in a particular way, virtual particles exert a slightly higher pressure on the outside of the plates than the inside. This pressure difference has been measured. Another more important effect is that virtual particles can cause black holes to evaporate. You may know that a black hole is an object of such high matter density that its escape velocity exceeds the speed of light, meaning nothing can escape from it. At least, that was the original idea. In 1974, physicist Stephen Hawking realized virtual particles might cause black holes to evaporate over time. Before Hawking's theory, black holes were thought to be repositories of mass energy that could only become larger over time by absorbing mass and energy from their environments. In this theory, now called Hawking radiation, virtual particle pairs come into existence at a black hole's event horizon. That's the normally impenetrable barrier between a black hole's interior and exterior. If one of the particle pairs cross the event horizon, this may split the pair apart, an event once thought impossible. This has the effect of creating two real particles from a virtual particle pair, one particle inside the event horizon, one outside. The result is that some of the black hole's mass energy escapes, which means black holes may evaporate over time. I emphasize that although accurate, this is a greatly simplified description of the physics. This process, as with all physical processes, obeys the first law. Mass energy is neither created nor destroyed. So Hawking radiation harvests energy from the black hole, which may become smaller over time. Before describing the zero-energy universe, I want to make a point about quantum physics. Many people think quantum effects can only take place on tiny scales, much smaller than everyday dimensions. But that's not so. Apart from the Casimir effect and a few other everyday examples, quantum effects can take place at any scale with a decreasing probability as the scale increases. One example of a large-scale quantum effect is the Schrödinger's cat experiment. In this textbook example, a radioactive sample, a Geiger counter, a vial of poison, and a cat are placed inside a box. The idea is, the box is sealed up so we can't see what happens. At some random future time, the radioactive sample emits a neutron which is detected by the Geiger counter. The counter breaks the poison vial and kills the cat. The idea is, the radioactive neutron emission is a quantum effect whose timing is indeterminate. Therefore, the cat's expiration is also indeterminate. To discover the outcome, we must open the box. But wait for it. Because the radioactive decay is a quantum effect, its timing is random in a quantum sense. In a conventional experiment, we would open the box to discover the fate of the cat. But because nuclear radiation is a quantum effect, the cat is in what's called a quantum superposition. It's neither alive nor dead until we open the box and observe the outcome. For word buffs, this act of quantum observation is called collapsing the wave function. There are some practical constraints that prevent the Schrödinger's cat experiment from actually being carried out, but the principle is sound, and it shows that large-scale quantum effects exist in nature. And the Schrödinger's cat experiment doesn't violate the first law. After emitting a neutron, the radioactive sample weighs a bit less. The universe's mass-energy ledger remains balanced. Many natural phenomena are thought to be affected by quantum randomness, including the weather, biological evolution and photosynthesis, even consciousness, although the last example is pure speculation at the moment with no reliable evidence. A digression. Apart from an unknown connection to quantum theory, the other issue with consciousness is that we have no idea what it is or how to reliably identify it. Consciousness is appropriately described as philosophy's hard problem. This is the topic of a future video. Evidence is accumulating that the universe has exactly zero net energy, a balance between positive kinetic and negative gravitational energy. This is not to say the universe has no energy. It has plenty, but in a perfect balance between mass energy and gravitation. According to this theory, the energy balance is maintained by the universe's expansion at escape velocity. Another line of evidence for escape velocity is the overall curvature of spacetime. Large-scale spacetime curvature is tied to the universe's rate of expansion. Stephen Hawking and a number of other physicists have written about this idea that the universe may have spontaneously come into existence in the same way that a virtual particle pair interacts with a black hole. This idea requires that the universe have zero net energy, and as we have seen, there's good evidence for that. So there it is, one explanation for the universe in its present form. This idea is by no means an established fact. That's not how science works anyway. But it's a plausible theory based on available evidence. Hank Green has a t-shirt that says science is about becoming less wrong over time. Less wrong, I like it. That's more like real science than most people think. Thanks for watching this video. Please like and subscribe. And be sure to post your comments and questions for two reasons. One, a science video like this is bound to leave some things unclear, things I'll be happy to explain. And two, the YouTube recommendation engine reacts favorably to videos that produce comments. So be well, visit again, and hold on, this video isn't over quite yet.